So hi everyone, good morning. In fact, good morning, afternoon, evening, whatever time zone you are. So welcome to another enriching session of our webinar series. As you all know, this series is designed to serve as a dynamic platform for our IITG community. And when I say community, I mean the alumni, the students, the faculty, and the staff. And this series is designed to engage with thought leaders, innovators, and experts in various fields. Our goal is to empower you with the knowledge, inspire curiosity, and foster meaningful connections within the community. So today, we are honored to have Rajeev as our esteemed speaker. Rajeev is a proud alumnus of the class of 1999 with a degree in mechanical engineering. He has illustrious career in the fields of automation and robotics. He has been at the forefront of innovation, holding 42 patents, and over 25 peer-reviewed research papers. Rajiv's expertise spans across multiple industries like semiconductors, robotics to warehouse automation, and while leading with the leading organizations like Siemens, Finisar, and Amazon. So today, Rajiv will be sharing his insights on robotic technology to enable next generation manufacturing. So this is a topic that is not only relevant, but also a transformative in today's rapidly evolving technological landscape that we see with the AI and other robotic advancements. So we strongly encourage you to participate in today's session. Feel free to submit a question in the Q&A section of the Zoom. Or if you would directly like us to ask a question, please feel free to raise your hand using the Zoom feature. Now, without any further ado, please join me in welcoming Rajeev. And please take it over, Rajeev.
Hello, everyone, and thanks for joining the call. Can you hear me?
Yes.
Okay, awesome. So let's just start with the agenda. So while I was thinking about this presentation, this being a very peculiar topic, I thought there's a lot of work being done, but some of it is mainstream, some of it is not yet mainstream. However, the impact is significant. So just to provide a context on and some understanding of this, I was thinking, how should I get started with the topic itself? So I overheard a couple of folks at my work who were talking to each other that hey, uh, 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 about some medicine that they were taking. So doctor had suggested to take the medicine in the morning. The other fellow said but across 24 hours it won't be as effective. So he suggested that the doctor suggested to break the pill into two and take one in the morning and one in the afternoon. So that gave me the idea. So let us talk about pills, and then I will go into the main topic. So, typical drug manufacturing, we start with the basic ingredients, which are crushed and blended and eventually manufactured in a tablet press, and then coated and packaged and delivered to us. And those manufacturing processes, what do they lead to? What you see on the left, that is how typical composition of the active ingredient in the drug looks like. The same material across, and once you consume in our body, the dissipation of the material, it is dependent on the total surface area.
Rajeev, one quick,
Yeah.
I'm not sure if you wanted to share your slides, but the slides are not being shared at the moment.
Oh, really? Okay, my apologies. I thought I was. Let's see. New share. I think I was. Okay, share. Can you see it now? You are screen sharing it, as it says. Or let
It,
me,
okay,
otherwise, can you see it now, or I can do the
yes,
entire
yes.
screen share
You are
itself
fine.
then?
My bad.
Okay,
Yeah, you're fine.
okay. So this was the this was the first slide which I showed, typical manufacturing process. You start with basic ingredients, like granulate them, blend them, and then for one of the final stage of manufacturing, you have a specific mold into which the tablet, the ingredient is tablet pressed, and then eventually delivered, packed and delivered. And which leads to this kind of composition where you have the material, the active material, the same composition distributed uniformly. And what's the limitation with this? So once inside our body, the total dissemination of the active ingredients uh, is dependent on the surface area available, as the drug dissolves. And you know if you go back to our math and physics days, it's the surface area reduces, so that eventually translates into the total ingredient that is being delivered to the body, so which continues to reduce with the size of the pill. So what if we can come up with a manufacturing method where we can tailor the composition of the material depending on the surface area as the tablet dissolves inside our body, like so that the distribution of material is quite uniform from from depending on the over cycle, whether it's 24-hour or 48 hours or 12-hour. And in terms of opportunity, you know so of the total drug delivery, it accounts for 1.5 trillion across the world, and 30% of those drugs are slow delivery drugs. And a method which will which would allow us to manufacture drugs in that manner will definitely, in a tailored composition, uh, will benefit from this technology. So with that background, why tailoring of the material, within the inherent volume, and a technology to do so, uh, will be revolutionary or uh, beneficial. So just a historical perspective, materials as well as the manufacturing processes, they allow us to build those useful stuff: shelter, tool, transportation, and as recreation and art. And and if we look at human history, it is the discovery of basic materials, invention of materials, as well as the manufacturing processes, which brought about revolutionary changes. uh, we started with the taking a piece of monolithic rock and breaking into a certain form to build handheld tools. And then some genius came along and they said, how about we add a lightweight wood to it, use materials such as thread, leather, or hair to tie those tools onto this lightweight material, so that increase the efficiency as well as improve the load distribution effectiveness. And from there, once the with the advent of electricity and electrons, I mean, with the with the discovery of those, uh, scientists and engineers came up with a way of controlling that electricity, building amplifiers and things like that, using in the initial phases vacuum tube, where you have heterogeneous materials that you assemble together to control the electricity, amplify the signals. But uh, the inherent limitations were again due to the material, the tolerances that you have to maintain all the things in vacuum, uh, and the speed at which you could modulate them, and which led to today, where we are blending semiconductor device, I mean, semiconductor material with the metal in one monolithic uh, piece, with much higher order of modulation and better control, uh, and uh, and enable many different technologies, things like entire computer in palm of our hand has been possible because of this. So with that, you know let us understand, what typical industrial product. I mean, taking an example of cell phone itself, its core functionality is communication, display, cameras for taking picture, memory for storage, uh, and uh, and yeah.
Um, is it okay if you can take one question? There is one question in the audience
Sure,
from the audience.
sure.
So the question was they wanted to understand what is the relationship of these materials to the surface area argument that you presented earlier.
Oh, so the surface area. So what I'm where I am, what I want to emphasize is like most of the, I will talk about those things later, but we are we are extremely limited, like by the manufacturing processes that we are used to, which is everything handling in bulk. you know we are not able to get to the inherent volume to modulate or like vary the composition at a smaller scale or inside the volume. So uh, drug was one of the examples, and the same thing applies in many of these our engineering products as well. If we can go tailor the composition of material inside the volume, we can we can make it more effective, um, we can make it more efficient, and this will open many areas of many opportunities. So slowly going there. Okay,
Thank you.
so you will see that everything will tie together. Okay, so you know different materials with different functionalities, and many times not just the product itself, because of the manufacturing processes itself, we take certain decision. For example, like on a cell phone, say these are four different components which are susceptible to electromagnetic interference. So we put some kind of agent, a covering or something for EMI protection. Now we could have a different EMI protection requirement for each of those. So we will add a lot of redundancy because we want to introduce, for ease of manufacturing, just one agent, and the properties of that will be tailored so that it can um, it can cater to each of these four components. And imagine if we would have a process where we could provide, where we could tailor the EMI protection for each of those individual components. We could get to that extent of manufacturing. So we will have uh, we will be able to probably manufacture much more lighter weight and much more improved performance. We'll be able to get much more improved performance out of that device. So you know what if manufacturing process lets us add a structural material where structural loads are critical, locally tailor the material for thermal electrical properties or EMI properties, and not just the material composition, but also the microstructure. And again, this takes us to the idea which I introduced earlier, think of pill geometry, where depending on uh, the rate at which the pill dissipates or dissolves, its composition continues to change. And in addition to the basic functionalities, some of the other advantages are like when you are assembling multiple materials, there are discrete interfaces between them. But when you are blending the material on the go, there's a gradual variation of properties. So while there are many other advantages, if you think of loads itself, if there is a structural load on the object, by preventing those discrete interface, you will see uh, improved structural integrity of the part. You can tailor the properties and enhance the performance. So existing manufacturing processes, we start with the bulk and we remove, either we use subtractive manufacturing processes or we use additive manufacturing processes, but everything is confined to bulk. We are not able to tailor the material composition, inside the bulk to the extent that we want. Yeah, maybe we can add the material, use a special heat treatment, but still it will be confined to the top surface maybe. So with this, like, you know, uh, I would like to talk about freeform fabrication. So what essentially freeform fabrication is: ability to control the material composition within the bulk, even microstructure distribution, and free-form features, ability to form features on the go as we are fabricating, manufacturing the parts. So you might have heard of 3D printing and things like that. They are classified as 2.5 axis based deposition. Uh, you deliver the material at a specific point. Uh, but like while there has been significant revolution there, still we are limited to adding the material in form of layers and a zigzag approach. Okay. uh, and with robots bring like an extensive articulability, like imagine 6 degree of freedom robot. You can approach the bulk. 3D printer will only come from the top, like material addition. Maybe you can pivot the platform to some extent, but 6 degree of freedom robot, it will allow end effector to approach the substrate from any direction. Okay. And by controlling the size of end effector, you can also control it- the minimum volume that you can access or deliver at any point. So now this is what I mean, uh, the idea which I'm talking here, this is not what I do on day-to-day basis. I were like my I develop robots or robotic type of systems for warehouse automation, or to some extent even in semiconductor industry. I got interested in this in early on, during my PhD days, and uh, I had about 2 years of experience in the industry, and I saw all these limitations. So I was extremely excited. Um, and when I went to my advisor, I we agreed on one arrangement, while all other students in the lab, they had picked one topic and delving deeper into and I suggested that there are 4 or 5 ideas that I have around this freeform manufacturing process. uh, I want to demonstrate the feasibility of some of the about 4 to 5 things which I have in my mind. And he was extremely excited and supportive about it. So my work at that point was limited to showing the feasibility of it. Later on, when I went to semiconductor industry, I applied this technology to solve some of the problems, and within the limitations of what I can share, I will show some of those examples. But I will show how the process planning aspect of it, and how I how we did it in the lab. And then I will talk about extensively about the opportunities and some of the things that are happening in the field. Okay. So the a typical part, it has geometric features, different material composition, and if we are using a phase transformation, like one of the critical thing is how we are controlling the energy, because energy is critical for the microstructure formation. So these are the 3 key things which I took and demonstrated the feasibility. I took a Motorman robot, 6 degree of Motorman robot, and and added a rotary and tilt table to it. We developed a powder feeder system. What you see, I mean, material feeder system. The material feeder system that you see here is actually this was commercial. It was limited in many ways, so we developed. I think at that time it was uh, one of the most precise and best resolution, material feeder at that point of time. So this is the platform which we used. Now, coming back to the process, you know, you can use 3D printing type of approach because you follow a zigzag path and you are adding the material depending on the size of the nozzle. Uh, 2.5 axis approach where you are adding the material in layers and you are following zigzag path. So the limitation with something like this is that I'm limited by the zigzag path here. And my composition of material keeps on changing from one point to another. Okay. And what are the problems inherent to it? So if you can see from the material feeding point to the robot end effector, there is a there is a carrier. So every time I change the composition, I have to wait to discharge the material which was inside the carrier, wait for the material composition to become stable, and then start to deliver the material at the point. So makes the process extremely slow, extremely inefficient, and lot of material wastage in that process. So thinking through that, I introduced something called Maxwell framework, where for sure we are blending the material on need basis. However, we discretize the material field, you know, we discretize the material field and handle in what I refer to as the Maxwell framework. And the size of each, just think of pixel, like the combination of different RGB, you can generate different colors. Similarly here, depending on the material delivery requirement and the minimum resolution, you discretize that space. Then take a volume, discretize it, overlap the material requirement. And now the significant shift was, instead of zigzag path, follow connect all the points which have similar composition and generate the path according to it. So with that, and obviously you have to take into account the limitation of the additive system itself. And the process becomes extremely efficient. And just to give a primer into the microstructure itself, it's the amount of heat coming in, the amount of heat going out, and the rate at which is happening decides what is the microstructure which will be formed. So the approach that we took was, I think I might have a little.
Rajeev?
Yeah. Yes. Somebody had a
Okay.
question. Yeah.
Prithvi, you raised your hand. You can unmute yourself and please ask the question. Prithvi.
Uh, I'm not able to hear. I don't know. It's just my technical problem, or you are.
No, Prithvi Raj Chauhan, you raised your hand. In case you have a question that you want to talk about, please feel free to do so now. Okay, maybe it's by mistake.
Okay.
So, please carry on, Rajeev. Sorry.
Yeah. So yeah, we decided to build at that point of time, things called lookup table. So what the lookup table was, here we go. So like we had a representative bulk, which is if my heat source, say imagine this is a bulk, and my heat source, we were using laser at that point of time, is here. I have 360-degree material around it. Here I have about 180%, 180-degree equivalent material. Here 90-degree, 45-degree, and so on. And then for the same heat, what is the impact, or the molten pool that we were generating. And by modulating the extent of heat and the equivalent geometry, we were able to come up with a lookup table that how much, what is the control in the that we have to do on the heat source, so that it stays uniform and the rate of cooling stays uniform, and I'm able to get the desired microstructure. The first application of this approach was uh, on another technology that we were developing at that point of time, which is called friction stir welding. So unlike regular welding where you melt the material and joining them, friction stir welding allows you to like overlap two materials and let a tool dip into it, and then plasticize the material and actually physically blend the two material. So some of the advantages of that is you can join copper to aluminum, aluminum to steel, things like that, which are not possible with the existing other welding processes. And one of the core requirement for the tool was we wanted the tool to be soft inside and the hard along the periphery, so that there's an effective mixing of material, um, and the material is hard enough to mobilize the material that it was welding. I'm referring to the tool material, whereas the soft inside, so that it could take shocks, if there's a mechanical shocks. And we took two material, tool steel and tungsten carbide, and then adding tungsten carbide from the approximately 0% to 20% as we make a transition from in the outer zone of the tool. And here you can see the microstructure. Going to the the geometric features itself. We introduced this idea called using morphological skeleton and geodesic rearrangement. So if I have to fabricate something, so complex, think of like, 3D printing approach. If I'm fabricating in 2D layers, there are a bunch of overhanging regions. I have to account for that. Maybe I could get creative by starting with the core, like, substrate material, and add one fin at a time, as you can see here. What the problem that it poses is, like, if I manufacture one fin on it, when I bring the uh, my material head, it will start to interfere with the material which has already deposited. So we use this idea that, okay, for each of these features, let's find what is the morphological skeleton, and then use that morphological skeleton to guide the direction that the material deposition head will follow. And also, depending on the size of the of the material deposition head, we will sequence. So potentially, like, we will say we deposit first 3 or 4 layers of the first blade or the fin here, then switch to the next one, and then switch to the next one. And when we are in the open, we do the continuous deposition. And taking all these idea to next level. So there was a challenge that NASA was trying to solve at that point of time, and they were considering uh, some approach to 3D manufacturing in International Space Station, like, in this space, because obviously if there is if you break a part, you cannot maintain inventory for every part. Like, if we could fabricate the part on need basis, so what helps manufacturing on the Earth is the gravity, but over there you do not have gravity available. So I took that approach to the next level, where by modulating the rate at which material is being added and the surface tension of the molten material, like, we can add the material in any direction. So what you see here is, like, one continuous spiral that we manufactured uh, over here. And then the next part shows additional degree of freedom that we are added, like, even in the radial direction we are varying. And for that entire spiral, we made it hollow, which adds another degree of freedom. Then we demonstrated adding material, like, this was the mother material in one direction, and the uh, another section which is horizontal. And then what you see here has been fabricated actually upside down by modulating all those parameters. So, you know, so demonstrated that feasibility that, blending the material, a path to blending material, controlling the basic parameters such as heat, at the same time, what we can do geometrically to be able to really free form fabricate the parts. And when uh, when I was in, like, semiconductor industry, like, one of the like optical subassemblies are used for, like, the optical fiber communication, and uh, the lasers which are used for modulating the signal, like, they are very susceptible to uh, environmental factors such as humidity or dust, and as well as electromagnetic interference. So the typical approach was that, what you see here. So uh, this is called can. Many of you might have seen it, and it has, it is a metal shell with the, like, opening on the top, and there's a pedestal here, and then electrical connections, like, coming out on this side. So you will pick up the laser chip from the wafer, assemble it here, and then after that, the this entire subassembly is further assembled onto a PCB, and then you bring an optical port in the like, on the front, which provides not only, like, which converges the laser coming from here onto the optical fiber, and at the same time, like, provides that interface. So we our scientists were, the scientists who were working with us, and at that time, like, the chip we were working was like limited to 16 GB. uh, when uh, our scientists developed like this chip which was good for for 32 GB, um, and it was robust enough to handle like environmental factors such as humidity and all. But still we were not able to utilize it because of the EMI requirements, electromagnetic interference requirements. So um, as it's and we realized that it was the number of electrical interfaces which was limitation. That is, the die is mounted on this substrate then gets assembled onto the PCB, so the number of interfaces. So if we could reduce those total number of interfaces, we could we could get to what we started for, which was 32 GB. And so we decided to go direct started we decided to going back to that whole experience, I suggested why not we go and assemble that chip directly on the flex. Let us see what those what those challenges are. While we were able to solve most of the challenges in this area, EMI continued to be a significant problem in this implementation. So then I went back to that idea of like blending the material on the go. We use what is called like a special kind of plastic called ultim for optical, which is optical grade plastic. And then and we have to maintain a the lens on it is some fourth order lens, like which is extremely difficult to manufacture, and we have to maintain very high tolerances. However, we went back to that approach where up to here we had like on these optical ports we had 100% ultim, and then we decided to blend a special material which was nickel coated stainless steel fibers that we blended in the material to provide that EMI protection. So going from discrete components to do so, we blended the material on the go. So eventually we were able to deliver the product. I would not, I will not be able to go into for detail beyond this, but just to suggest that starting from that idea of blending the material on the go at like at certain resolution. So this was one of the like an industrial product that we manufactured. Uh, I think like with that there are many applications. What I'm putting here is like I just uh, took it from some of the papers that I had read, like aerospace and defense, even in healthcare or energy, manufacturing and construction. Like they will all find application of this. But few things which I wanted to talk here was like so in terms of opportunities. uh, Semiconductor industry, like especially for the sensor development, like MEM based sensors or SAW based sensors, like they account for about 37 billion or so. But we are still limited to that 2.5 axis approach for manufacturing. you know as a simple example, like think of accelerometers. Accelerometers, yeah, in one direction is great, but however, as soon as you want an accelerometer for X, Y, and Z, all three, like we still are dependent on that, like 2.5 axis, like one directional approach. Now you know we can using this approach we can manufacture or those basic sensor to be effective along all three directions. Another one is like in electronics manufacturing, many times for heat dissipation we have to put a fan on it. This is just again an example, um, which will be most obvious. So say if I manufacture a PCB which is about 2 inch by 2 inch, however, there is a component which is susceptible to heat. So I have to put a fin and a fan on it. And the industrial catalog presents me a fan which is about 1.5 inches. Uh, and I am limited by what's available, like in the industrial catalog. So I have to reserve that space, 1.5 inches, and then move other electronic components. And suddenly, and like my PCB, which was 2 inches, it becomes like potentially 3 inches or 4 inches. So there's a lot of work being done, like where many of these actual mechanical actuators, such as fan and things like that, can be directly printed. What Another thing that it does is, uh, while picking the component from industrial catalog, we also build in a lot of redundancy. How about, like, depending on our need, we can print the fan, or we can print that actuator optimized for exactly our need on the spot. So it optimizes the process, like, energy consumption, keeps our, PCB, whatever, like, lightweight. The total, the total power consumption is also optimized. And then form factor above everything, like, the form factor as well. That's another example. There's a lot of conversation, a lot of things happening in the field of, like, silicon photonics and things like that, where instead of discrete component being connected from point to point, just why not print everything, like, directly there. That market is, almost 70 billion. It will be 70 billion by 2027. Uh, I already talked about, like, medicine and drug delivery. So, but uh, you know, w- one of the fields that will definitely benefit from it, and there's a lot of work that is being done, is prosthetics and tissue engineering, or medical implants. So, and quite often, like, titanium or some kind of inert material is used for that, or, like, specific type of ceramics. However, because of the limitation of the manufacturing process, we are still limited to the composition of the material. Imagine, like, if I'm manufacturing a replacement bone, typical bone, like, you have a microstructure in the center, which is different because of the fluids inside and the outer surface that engages with the muscles. The microstructure is different. But because of my manufacturing processes, I'm still limited to fabricating. I mean, I can use ceramic, I can use titanium, whatnot, but still the composition will be uniform through and through, which presents many limitations. What if I can blend our material? What if I can use the robots or this freeform manufacturing approach to exactly manufacture, like, uh, that bone, uh, to mimic exactly the, behavior of natural bone at the microstructure level as well. Um, I think I went a little bit over half an hour, but yeah, at this point, those are the things which I wanted, like, you folks to get excited about. Um, uh, and I continue to work in this, on my own, and following all the work that is happening in this field. Once in a while, I'll engage with, the folks who want an insight into it, or, want to try run an idea by me. But yeah, at this point, I'm open to take, like, any questions that you may all have.
That was awesome, Rajiv. Even it was mind blowing for me to learn that just behind the materials there is so much happening.
Yeah,
Uh, there is so much space for innovation. We just think about metals and manufacturing, but you delved into freeform fabrications, FGMs, functional graded materials, and other innovations that you worked on. And the last one that you talked about, the foam part as well. Um, that tells us how much space is there behind each of these concepts. Even the concept of manufacturing, there is so much geometry behind it. There is so much math behind it. That's very enlightening to learn. I had a question here.
yeah,
So you talked about the limitations of existing manufacturing processes, right?
yeah,
Particularly challenges like bulk material handling and process accuracy. So, and then you delved into freeform fabrication, showing that freeform fabrication is a delta improvement over existing processes.
right.
Um, but so how, because your techniques are used in space and aerospace industries where precision is very important. So how does the freeform fabrication help in these high precision industries?
Uh, so, like, there are, I mean, freeform fabrication, like, over there in aerospace industries and places like that, like, you are fabricating the same kind of parts over and over. So, essentially, the manufacturing, they can afford to develop the implements like for that specific products, like we have very high order, like multiple degrees of freedom of CNC machines and things like that, and then you manufacture the core, and then after that you can afford to you know uh, uh, to perform those, like secondary processes on it. So there is a significant, like number of dedicated machinery to that. Now, said that, those processes continue to be extremely inefficient because, and they are based on what is referred to as lookup tables. And I think uh, we can enhance the efficiency of the process by, now instead of referring to those lookup tables, uh, ML or AI, and we can, uh, and instead of working in a passive, first of all, like, you can make that lookup table rich. At the same time, you can enhance the effectiveness by monitoring on the go and controlling the parameters. Yeah.
Right, right.
Yeah.
So you're bringing the problem into the software space now by parameterized.
Yeah. Yeah.
So there is another question here, Rajiv. It says
Yeah.
that your presentation highlights the potential of FGMs
Yeah.
in fields like healthcare.
Yeah.
Can you elaborate how robotics is enabling the development and application of these materials in real world scenarios?
uh, so I mean, one of the most basic things that, I mean, that has happened recently and has been extremely effective is, uh, I think, depending on the implants that you want in the body, uh, I won't go as much in the functionally graded, like, part. I mean, that is one component for sure, but more in terms of, like, freeform manufacturing itself. Uh, so, you know, every person has different type of bone structure. Like, if you want to put an implant, like, it has to be titanium based, and the most of the existing processes, they were based on what is called subtractive manufacturing, and that makes it extremely complex and very long term, like, and expensive. So there is a technology, like, which was recently introduced, which is actually electron beam based manufacturing, which allowed the 3D printing of titanium material. So with that, what happens is, depending on every individual's need, whether, like, you want a piece of a skull being replaced or knee implant or anything like that, you can take the 3D model of the individual's requirement, feed into that electron beam based manufacturing system, and you can just, in a day, be able to uh, fabricate that part based on the individual's need, and with, like, minimal whatever machining or post processing that is required. In functionally graded material space, yes, uh, uh, there is a lot of work being done, like, tissue engineering and things like that, that you might have heard about, but it is still a bit far from, the scale that we want it to be. Where uh, uh, where they are blending, like, uh, the structural elements along with the live cells. So as the live cell grows, like, it consumes those structure and then form, you build organs and things like that. But again, it's still in very, very basic phases. Yeah. So that's where, like, we are blending the material was the second example. First one was the freeform manufacturing. Yeah.
Got it. Got it. So one other question we have here is, in your discussion about submicron manufacturing and tailored materials,
Yeah.
you mentioned that the potential applications in areas like semiconductor technology and drug delivery systems.
Yeah.
So what are the key challenges in scaling these innovations for industrial use?
Yeah.
That's the question.
Yeah.
Yeah.
So uh l- like the challenge that has been, like, and I think, like, there are many agents who are solving this. When I was grad student and when I was approaching all these problems, I was limited by the form factor of the robot itself. Like, I could not
Mhm.
imagine, like, going to the wafer level and adding the material in any direction. Actually,
Yeah.
at that point of time, I wanted to develop a, like, spaces specific like piezo-based material for certain actuation which I wanted, but it just I was limited by the robots at that point of time. Now, I mean, you see, there's a company called Macadamic or CPC. They are manufacturing extremely small form factor robots with micron order accuracy. So, uh, uh, I mean, at the same time, controlling those parameters, we had to spend hours and hours, days of work in just coming up with those lookup tables. You know, you perform you perform extensive uh, what to say experiments to come up with those rich lookup tables, but eventually uh, you know uh, still the implementation was feed forward, like means, okay, I feed these parameters and hope this is what is happening. But now development of so many sensors, and probably AMI and ML can close that gap. You can really tune the parameters to nth level to get the quality that you're looking for. So those were the challenges. As I said, the form factors of the actual robotic hardware and things like that, and the sensors. But now uh, we are closing that gap. There are a lot of opportunity. And actually, you should look up that Macadamic robot. It is expensive, but it's just like little cute robot. I'm planning to get one for myself at home. Yeah,
Awesome, awesome. I will certainly take a look at that now.
yeah.
Um, yeah, any questions from the group that you want to directly ask Rajiv? I'm happy to unmute you and you know, allow you to speak.
Uh, no, I mean, yeah, I'm here to answer any questions you might have. I'm always excited about the things that are happening, and not typically limited by what I do on day-to-day basis. Obviously, without crossing those boundaries, uh, w- as you can see in the back, my garage is a lab. I continue to work on these things and experiment on my own as needed. Yeah. So I'll be glad to talk if anybody should have any questions, or you just want to run an idea by. Yeah.
Uzair, I unmuted you in case you are able to talk.
Yeah. How's that?
Hi, Rajiv. Thank you very much for this very
Same.
exciting presentation.
Yeah.
Um, I wanted to know when you propose changes to industrial product manufacturing, would this increase the number of steps, or do you have some ideas for doing the focused placement of components using the same number of steps that we currently have?
Uh, I mean, it will depend on the product, obviously, but given that we have higher order of uh, articulable articulability, I think the total number of steps we should be able to reduce them significantly. I'll just to give an example. It's we were uh, the in one of the manufacturing processes, we were extremely limited by maintaining the orientation of some of the dies. And what we would do is we will add additional step, because we had one manipulator. What it will do is, it will orient the substrate versus the the that die that you are going to attach. Will put a special kind of dye, a special kind of epoxy. And in order to maintain the orientation, it was ultraviolet sensitive. We will shine ultraviolet and zap it there. And then we used to have a secondary process where we would apply another epoxy and treat it so that you know it it maintains that orientation through the life. But now I can see how we can eliminate that the first step by effective use of those small robots. Uh, uh, so yeah, for most of it, I do speculate that we should be able to reduce the total number of steps. But again, it also depends on the product to product. Yeah, I don't know if I answered your
Understood.
question, but yeah, yeah,
Yes, yes, understood.
yeah,
Thank you
yeah.
very much. So in all, for all of the steps, the substrate would stay on the same manipulator. Is that right?
Actually, uh, yeah, that will, yeah. to say the least. However, like, we are actually, I am personally like also experimenting, like, having substrate on one and the die to be added on two different robots, and you can orient them as needed. So it's like, two
Wow.
robots dancing, depending on my geometric requirements. Yeah.
Wow. Thanks very much.
Yeah.
Any other questions from the group, please? I'm happy to unmute you and you can ask. Okay, while you're thinking, I have one other question here, Rajiv.
Mhm.
It is mostly, you talked about many innovations, a lot of opportunities in this space. So for our entrepreneurial group of people in our alumni, uh, what should they be looking at? What are the niche markets and specific problems that are currently existing out there, which the entrepreneurs can pick up and start solving?
Okay. Immediately, I think that drug delivery. I mean, you take a like, actively blending of materials and adding in a way what I showed, like in one of the first example. Th- that is a great
Yeah,
opportunity to start with that. And in addition to that, like, providing, industry is limited by what is available out there. So okay, I mean, since I got 3-axis CNC or 6-axis CNC available, you know my manufacturing process will follow that. However, like, if you marry, there is a significant opportunity in marrying whatever is happening in AI space, ML, along with the sensors and the actual mechanical hardware. You just the you like, you open up a lot of opportunities there. I mean, there's a lot to be done there. I mean, without uh, giving out too much, uh, many of these. Uh, Many of the automations, actually, many of the automation continue to be manual just because, our manipulators are not able to do the same thing over and over. They are not able to get to that resolution. Um, and because of the and some of the uncertainties there. But with the growth in sensing and ML or AI based, like, control, if we close that loop, I mean, there's a revolution about to happen. Yeah, I would say.
I see.
I mean,
Awesome.
and many of the other things, like, we have to start thinking a little bit out of box in just think of electric vehicles, like, just to give an idea. We are still thinking electric vehicles from the with the same lens that, how the first vehicles were manufactured. That yes, you got an engine somewhere, a source of power somewhere, and you need to provide a basic structure and all the kinematics. And then, as I said, like, source of power, like, just like what we have a gas tank, you know, uh, here we have a battery located in one place. Just think about it, like, if I can totally optimize the vehicle, because the battery, each of the individual battery has some structural, like, component to it. How about if I, in addition to battery providing the power supply itself, like, I can uh, embed it along with the structure itself. I have batteries, all over. I can make the whole thing so efficient. But because of the manufacturing process, like, battery here and, kinematic chain here and the structure here, like, I have to bring it all together. If I'm manufacturing things, uh, like, on the go,
Yeah,
I can blend all these things, and suddenly the weight becomes a half of what it was. I can place the things on need basis, like, I do not have to have wires running from battery to the motor, and whatever losses are there, I can place mm, like my power supply right there, next to the wheel, and things like that. But again, it will require very, very out of box thinking. Yeah. And the thing
awesome.
is, we have manufacturing methods to support it now. Yeah.
I see. And all the techniques that you just talked about, Rajiv, are they done by Amazon itself, or are you preparing the processes for other larger manufacturers to manufacture them?
Also, none of it pertains to Amazon. This is just purely out of interest. And I continue to work. Many of these ideas which I presented, I have been approaching. Following my research work, like during my PhD days, I continue to work with the small inventors or by myself. I've been presenting a lot of these works in different conferences as well. Actually, last year I worked with a group of kids who wanted to manufacture uh, the like in hobby grade um, the motors for the hobby grade rockets, and they wanted to develop their own ceramic. So we developed entire like robot based axisymmetric manufacturing process for them to test out, adding blending different materials and making those complex geometries. So mostly, yeah, on my own. Obviously, if it was Amazon, I would not be able to share any of this information. Yeah.
Gotcha, gotcha. Thank you, Rajiv, for that. Dhirendra, please go ahead.
Yeah.
Hey, Rajiv,
Hey,
thanks for
Dhiren.
this session.
Sure.
Good to speak to you here as well. Yeah, I mean, I just wanted to send a note that I remember IIT Guwahati, you were one of the person who inspired me to pursue robotics also, although I could not pursue as much as you did. So, but good to see your presentation. Uh, Question,
Thank you.
Rajiv. So I'm interested in knowing your thoughts about uh, sort of swarm robots, meaning small robots, and there are multiple applications, right, where they could be useful, be it ocean plastic cleaning to any other, like security thing in schools, shooting, this, that, so sort of monitoring it, swarming on it. They may be less costly individually, but they're like
Yeah.
100 robots, small robots, and they accomplish bigger tasks. 20 years back when I was in my master's, I was doing different projects. That time I saw some research happening, but I was expecting it'll take off big time. I am not sure what is the current state. But how do you think, swarm robots can help, and are they a good idea? Are they flying? Are they happening, or is it like a theoretical concept and not much used?
Uh, no, it is a great idea, but again, like, the real problems that we have to solve in the world, like, they are more about how we can solve it in the most efficient manner. So many
Mm,
of the ideas, many of the problems that we were trying to, that folks were trying to solve with the help of swarm robots, uh, by standardizing a lot of things, we were able to solve them with the existing solutions that we have.
mm,
Uh, however, uh, actually, I was very curious to see if we will be able to see it like, within next 4 to 5 years that, any, uh, those drone shows, will,
mm,
will we be able to really implement that kind of control and coordination between them? But it has, at least for me, it has blown my mind away. So now technologically we are there, and many of those applications, I guess they can compete with what I was referring to as this, by standardization, we were solving those problems. So some robot, definitely they are more pertinent to many problems, and it was the technology which was limiting it. But I think, yeah, uh, yeah, they will find acceptance in many fields. They will definitely find acceptance in many fields, because even with the standardization of hardware and other things which I mentioned, you are still limited to that
mm,
limit rigid structure. With SOM, it is fluid, true free form, and you can adapt to the existing problems. So yeah, um, uh,
mm.
many opportunities there. Yeah.
Got
I don't know
Thank you,
if
Rajiv.
I went too much
Yeah.
theoretical, or did I answer your question or not? But yeah,
Uh, yeah, I
yeah,
think it's a good active debate discussion, and you're right in that direction. I'm just wondering, like, all this, when will it really come out in practice rather than in labs? Like labs, there are a lot of research, and I'm just curious, like, how will this take off? And you're right, there are other multiple dimensions: cost, adoption, public adoption. There are other ways where it can be solved.
yeah,
So
yeah. I mean,
That is
without
good.
divulging, without divulging too much, like, something, I can give you a context. It's within the warehouse industry, like when it is a regular product you are manufacturing over and over, the form factor is same, the same kind of packages, the same
Mm,
kind of objects you are handling. But today people want, like, television to be delivered to their door, like, a little Lego for their child also, and the same companies who are delivering. So when you go to the warehouse side, it's like you have the same equipment, but you have to handle things from 49 inches to 4.9 inches. And v- that is why there is so
mm,
much of manual labor, because those machines cannot adapt quickly to the two, or you have to establish separate process path to handle them. And now with the what swarm and these kind of robots can bring is like they can adjust to the uh, the package or the material or the
mm,
weight that you are handling. So definitely, like, if we can bring the swarm robotics in a very in somewhat cost effective manner, I mean, it can match the the price that we pay for manual labor any given day. Yeah,
mm. Good. Thanks, Rajiv.
sure. Anuj had a question. Hi, Anuj.
Yeah, Rajeev, hi.
Hi.
Uh, Hi, so I graduated in 2017 from
Okay.
IIT Guwahati, and I was just like interested in the swarm robotics conversation that Dhirendra brought up.
Right.
I actually worked on the same application. So I did my PhD in University of Washington, Seattle, where we were using multiple robots to carry, let's say, composite structures
Right.
in on the factory floor. And the main problem there was the same thing, that these structures can be as long as 60 feet long, and they are very flexible, and you have to move them very slowly. And
Right.
there are very, let's say, fixed technologies, let's say, based on hanging off the roof of the warehouse, where they have these, let's say, tugs that they use. So we propose a solution based on multi-robot networks.
Right.
So cooperative object transport on factory floors using multi-robot network. So it is finding applications there.
Right.
So when you say swarm, I think about it in terms of, let's say, n greater than 20, 30, something like that.
Right.
But let's say the same concept, when n is, let's say, less than 10, we usually call this in the literature multi-robot networks,
I see.
and it is finding application in manufacturing.
Right. Yeah. Yeah. Thanks for that note. Actually, g- uh, it is a great insight even for me. Yeah. Thanks. Yeah.
Yeah, thanks.
I think Dhirendra has another question, I think.
No, I'm good. I think I didn't lower my hand.
Yeah. Okay. Vikas, if you're talking, you're on mute.
I am on mute, yes. Any other questions, please, from the group? I'll just stay here for another 30 seconds before I wrap up the call. And Rajiv, if the people wanted to talk to you or reach out to you, what is a good channel and a medium?
Email is email should be good. Yeah. You can use my personal email. Yeah.
Okay.
Yeah.
And if you can share that with me, I will share it along with the recording of this webinar later.
Okay. Okay.
Uh, that that is good. All right.
So
I think that's all
sure.
we have. Sorry, Rajiv, did you have anything more to say?
Oh no, you want me to send it now, or I can send my email afterwards also?
Yeah, I mean, I will post it along with the webinar, or you
Okay.
can put it into the chat as well so that the people can take advantage of it.
Okay. Sounds good. Yeah.
All right. So that was that. And thank you, Rajiv, for the very insightful and thought-provoking session. And this advancements in robotic technology and next generation manufacturing has certainly provided us with a wealth of knowledge today. I hope it is useful to the alumni. And it has sparked new ideas among us. The entrepreneurs can pick up some ideas from what you just discussed with us, and they can solve those pain points as well. So before we close, I had like to remind everyone that your participation is crucial as always. So please provide feedback on the session. And as Rajeev just said, if you have any questions or if you would like to interact with him, please reach out to him. His email will be shared along with the recording of this session. And yeah, I think let's continue the conversation beyond this webinar. I would encourage everyone to stay connected, stay curious, and keep exploring. Thank you for joining us today. And until next time, take care and stay inspired. Thank you all.
Thank
And
you.
thank you, Rajeev.